Okay, everyone, it's 11 o'clock, time for the next session. This session is past and present solar system session. It is my great pleasure to do chair at this meeting. I'm Hikaru Yabuta from Osaka University, Japan. In my introductory talk, I'd like to outline analytical chemistry of building blocks of solar system and life. First of all, I would like to introduce my co-chair Daniel Lazaro and all the speakers from a variety of studies about Europa, Mars, Titan, and primitive small body materials such as IDPs, IDPs and comets and meteorites. So 4.5 billion years ago, our solar system and primitive small bodies, meteorites, comet, interplanetary dust particles were formed by accretion of gas and dust that consists of mineral and organics and ice mantle in interstellar cloud. Astromaterial science is microscopic approach for understanding for the origin and evolution of building blocks of the solar system. And this approach includes anatomical investigation and comparative meteorite study and sample return space exploration mission. And also this approach has a complementary relationship with a macroscopic approach, astronomy. Organic analytical techniques have been dramatically improved very recently, as summarized here, which has made it possible to measure very small abundance of the extracted soluble and insoluble organic material from meteorites, as well as their molecular and isotopic composition precisely. About a chemical analytical series of insoluble organic solids, I think this afternoon Sylvie Dehen give a talk about this. And also, very recently, lately, direct in situ analysis of organics from cometary and interplanetary dust particle by state-of-art techniques such as spectral microscopy and isotope microscopy. I think this afternoon George Flynn will give a talk about this. To understand the origin and evolution of organic matter in meteorites, comparative meteorite organic chemistry is very important because the classification of meteorites is based on the different degrees of physicochemical effects, such as parent body aqueous alteration and thermal metamorphism driven by radiogenic elements and shock metamorphism. This chemical history of the early solar system is recorded in the variations of molecular and isotopic composition of organic matter. I'd like to show a good example of the molecular variation of soluble and insoluble organic matter in relation to parent body aqueous alteration. In the right figure, Cody and Alexander's solid-state carbon-30 enamel study of insoluble organic material from different meteorite groups shows that the degrees of aliphatic carbon is reflected by the extent of parent body aqueous alteration. Also, in soluble organic compounds, amino acids abundances and composition and homochirality appears to relate to parent body aqueous alteration. Martins and Ehrenfreund have reported that amino acids are the most abundant in the least aqueously altered meteorite groups, while they are depleted in more aqueously altered meteorite groups. Also, Gravin and Dworkin have reported that large L-enantiomeric excess of isovalene was observed for the aqueous altered meteorite groups, but it was not for pristine meteorite groups. Our past study has investigated that the insoluble organic macromolecule from the thermal metamorphosed chondrites shows the X-ray absorption feature of highly conjugated sp2 carbon, such as graphene. This peak intensity of graphene increased with meteorite petrologic subtypes and were used as a thermometer of the peak temperature of the parent bodies. This data is nicely consistent with the Raman spectral data by the different groups, Bonaru and Kiriko et al. Based on these variations, recently, comprehensive studies of mineralogy and soluble and insoluble organics from the 4 distinct fragments of the Tagish Lake meteorite have been conducted by Canada and the United States collaboration group. Both soluble and insoluble organic matter show a large variation in molecular and isotopic composition, including amino acids enantiomeric excesses, and they discuss that such heterogeneity in organics in the same meteorite may be evidence of the influence of the hydrothermal processing on its parent body. So it has been also experimentally studied that hydrothermal processing modifies macromolecule and produces new molecules. So far, several experimental studies have reported the production of polycyclic aromatic hydrocarbons, acetic acids, dicarboxylic acids, heterocyclic compounds by hydrous heating of macromolecule. And the recent study by Pizzarello reported the formation of highly abundant ammonia from macromolecule from the less altered meteorite groups. So these new molecules may have been involved in molecular and isotopic variation resulted from Tagish Lake and other parent bodies. The use of the ion probe mass spectrometry has enabled the detection of the isotopic anomalies from macromolecule from meteorites, precursor of meteorite organics material, regarding that it forms a similar superior to organic globule and similar molecular composition to meteorite macromolecule. On the other hand, Hashizume et al. Have found the coherent enrichment oxygen 17-18 and carbon 13 enrichment in macromolecule that is not consistent with nitrogen and hydrogen enrichment. They discuss this oxygen hotspot can be explained by its formation due to the photodissociation of carbon monoxide in a gas medium at higher temperature than 60 Kelvin. That is solid origin. So open questions are how is organic molecules associated with minerals and water that is originally distributed in meteorites or comets and IDPs? What is the intact composition of organic molecules in meteorites? What does the diversity and heterogeneity of the organics imply? And how are soluble and insoluble organics related each other? This information tends to be lost more or less during the extraction process. So in this point, a direct in situ analytical technique without isolation process is necessary, as well as isolation techniques. This is a distribution of carbon, calcium, nitrogen, oxygen, and iron of the Murchison matrix obtained by different X-ray energy using a synchrotron-based scanning transmission X-ray microscopy. You can see a carbon-rich area as a white, bright color region. And comparison of the elemental maps reveal which element is associated or not with the organic carbon. In this image, oxygen and iron is partially associated organic carbon. Also, we have figured out the originally directly observed organic carbon showed more aromatic feature than isolated macromolecule, and also heterogeneity in the several different regions in meteorite matrix. So we think this indicates the possibility of local fluid chemistry during the parent body aqueous alteration. Sample return exploration missions are the advanced version of astromaterial science. So far, we have two successful examples. One is NASA's Stardust mission for collecting cometary dust particles, and another is Japanese asteroid sample return mission, Hayabusa. From Stardust mission, we were able to learn the relationships between comet Wild 2 and meteorites, and also combining inorganic chemistry, we were able to learn material circulation in the solar system. In the Hayabusa mission, organics material have not been detected yet. Nonetheless, inorganic cosmochemistry have first time confirmed, first time have linked between the meteorite and source asteroid. And as introduced in the Tuesday night panel, future world missions will be coming. For example, OSIRIS-REx, Hayabusa 2, and studied mission Marco Polo R is planning to go to a carbonaceous type asteroid targeting organics and water or ice. So I'm gonna close my talk. Molecular and isotopic composition of organic compounds in primitive small bodies are important indicators for origin and evolution of the solar system. Parent body processing is a chemical factory that determines the precursor material that could have been delivered to the early Earth by primitive small bodies. Sample return missions improve our better understanding of information about locality, volatiles that may have been at least partially lost from foreign meteorites, and of generality and diversity of organic chemistry in space. Thank you very much. And I'd like to introduce the next invited speaker, Kevin Hand, Astrobiology of the Outer Solar System, Origins in Icy Worlds.
Thank you very much, Hikaru.
Thank you very much.